Good morning, sir.
Hello, can everybody hear me?
Yes,
Yes.
please.
Yes, sir.
Okay. So my name is Derek Emmanuel, and I'm supposed to take you through this course, computer architecture. And in the process, if you have any questions, you can just raise your hand, and we try as much as possible to clarify all the doubt. And if you're not talking, kindly mute yourself so I don't disrupt the class.
Okay.
All right, so you can proceed. So can anybody give us a brief idea or overview of what you think about computer architecture? Ali, you registered for the course, so I believe some of you know what it is. You can just raise your hand and then I'll ask you to proceed. Yeah, anybody? I realize some of you join and put the phones away and walking about, so let the class be interactive. Anybody to help us? Brief overview of computer architecture. Kubson Richard.
Yes, sir. Okay, sir. If we say computer architecture, my understanding is the interconnection of components coming together to form a computer.
Richard, are you talking? We can't hear you.
Oh, sorry, sir. Yes, I'm talking, sir.
Okay.
I said a computer architecture is the interconnection between components to form a computer.
Okay. All right. Thank you so much. Anybody else? I have another hand. Elliot.
Say hello.
Yes, talk to us.
I think computer architecture has to do with the hardware components and how they are structured and to work together.
Oh, okay. Thank you so much. We have another hand up. Yeah, or say.
Yes, sir. Computer architecture is the design, organization, and functional definition of a computer system hardware.
Okay, I believe you didn't read for us. Okay. Anybody else? Is that all? Okay. Yeah, your hand is still up. Some more.
Yeah, so they are the various components, or they are the hardware component that comes together to form a computer to perform function.
Okay. That's fine. Yeah. Do you have some other hands up? All right, so let's proceed to what I have here for you. And what some of you said are accurate. And when we talk about computer architecture, we are basically talking about how the various components of the computer system are actually created. And when we talk about component, we are mostly talking about the hardware part of the computer system. The hardware part of the computer system and how they are interconnected to perform their specific or specified function within the computer system domain. And then when we talk about computer architecture, it mainly includes machine organization, which is how the hardware component within the computer system are organized, interfaces that we interact with, applications that runs on those hardware, technologies, measurement, implementation, and some other simulations that we have. So these are some of the components when we talk about computer architecture: the machine organization, interfaces, the applications, technology, measurement, implementation, and in a way, simulations. Moreover, it can also be data format and instruction set design. Data format and instruction set design. So you realize that previously some machines are designed specifically for some data formats, and others are not. So in the process of designing the architecture of that specific computer system, you more or less tailor it to the data format that you want the computer system to emulate. And also instruction set design. What are the instruction format that you give to the hardware that you are designing to make up the whole of the computer architecture? So basically, this is what we talk about whenever we are talking about computer architecture, organization of how interconnected the hardware components are to create the computer itself, and also to satisfy functional and then cost goals. Mind you, in designing this computer architecture, cost is involved because the materials that are used to design the hardware component are purchased. And in the process of designing the architecture, you make sure that you satisfy the cost constraint that you have, and also it should be functional. That is a hardware that you manufacture or design should be functional. And you bear in mind the cost as well. All right. So now let's move on and talk about generations of computers. And ideally, when we talk about the generations of computers, we, most cases, talk about the various architectural design of the computer system. Those are what we normally measure when we talk about the generations of computers, the architectural design. And for the first generational computers or architectural design, the architectures of those computers are built on vacuum tube technology. And in this era, there was nothing like a central memory unit, like what we have today. So notice that the first generation, they were using the vacuum tube technology architecture. Yeah. Cliff. Is it Clifford? Your hand is up. All right. And then for the first generation, these are some of the features that came along with the first generation. So we had the electronic emitting devices. We have the data stored in single read-write memory. And then we have programs of instructions that are executed sequentially. Joseph.
Yes, sir. So with the slide you are showing, I don't know whether it's a typo. We can see features of the fourth generation, but we are talking about first generation.
Sorry, that's a typo. Yeah, that's the first generation. Yeah.
Okay.
Right. And then some of the examples are what we have, like the EN, IAC, and then the UNIVAC, which is the first computer. I mean, the first commercial computer that was ever produced. Right. So just notice that in the first generation, we have the vacuum tube technology. All the architectures of those computers during that generation were using the vacuum tube technology in their implementation. Right. So let's talk about the. Please give me some few moments. I'll be back. And then it's something. All right, thank you. So I just had to go and change the names to reflect the actual content, right? Thank you so much. All right, so as I was saying earlier, the first generation, basically, these are some of the features that it came along with. The electronic emitting devices, data stored in a single read-write memory, and then programs or instructions that are executed sequentially. Unlike these days, what we have for parallel execution and all those stuff. Earlier on, it was just sequential. One process has to finish, or one instruction has to finish before the resources are released to the other instruction that is coming through. And these are some examples during those age: the electronic numerical integrator and computer, and then the UNIVAC, which were the first ever commercial computers produced. All right, so moving on to the second generation. This is when we actually started building the operating systems. Fabina? All right, so this is where operating system was discovered and But then the only issue is that it only had the ability to perform or handle a program or task
Hello, sir.
once at a time.
Hello.
Hello?
Yes, sir. I wanted you to elaborate a little bit on the vacuum tube. What does it mean?
Hello?
Yeah, hello.
Yeah, you were saying
Hello.
something.
Yeah, I was saying the vacuum tube.
Okay.
Yeah, I wanted you to elaborate a little bit on that.
Okay, but did you do science at what's the name? Basic school.
Yes.
Yeah, so it's the same technology that was used here. So realize the vacuum
Oh,
tube
okay.
is more or less like a sealed glass or metal tube containing these electrodes or electrolytes, which is in a vacuum. So the vacuum just allows the electron to move more freely between the electrodes without them colliding each other. So that is the same principle that we use in this particular vacuum tube technology.
Okay, so does that mean that there were no monitors or stuff like that?
No, there were no monitors. No.
Oh, okay.
There were no monitors here.
All right.
All right, Charles.
Sir, good morning. Sir, my question is on the year in which the computers were created or was into establishment. The first generation, based on after reading other books,
Yeah.
I find out that the year range doesn't comply. This one is different from the one I've seen in different textbooks, including the second generation too and the rest. So I'm asking at the end of the day, which one is accurate?
I didn't get your question. Can you come again?
My question is on the year range in which each generation of computers was established. And I said, comparing what is here and other textbooks and research, all the year range, they differ. So I'm asking which one is more accurate or which one is expected for us to write when it comes to exam.
Are you talking from? I'm coming. Let me. Are you speaking from the modules you have?
Yes, please. Yes, please.
Yeah. So there are so many ways to more or less group these computers into their generations, right?
Okay.
But this is specific to computer architecture.
Oh, okay.
Right.
Okay.
Yeah.
Okay.
So there could be different criteria that we use to group the computers all together in the form of generations. And this is how the architecture was built, how the components were interconnected so they can communicate or process any other data information.
Sir, please, I'm not getting you. I don't know if you got my question, but I'm also not getting yours.
No, I'm not getting you as well.
I'm talking about the hearing. You see, on this one, they wrote 1940 to 1956 or so. Okay. And I'm saying that this hearing is also different from the other ones that I've read, even online. If you ask the hearing in which the first generation came into existence, they will tell you 1946 to 1959.
1946 to 1959. Okay.
59. And giving an example like the ENIAC computer is one of the first generation of computers that came into existence.
Yeah.
So I'm asking, that one, is it different from this one? Is it because this one is computer architecture? That's why they are saying that it is 1940 to 1956.
Yeah, so you more or less have to read and think about how are they creating the generations.
Oh, okay.
I don't know if you get what I'm talking about. So if it is based on the structure of the architectural design, then you can move further and then be in line with what you have in the book. But if it's a different way, then you can go by what they are saying. I don't know if you get what I'm saying. Because there's so many ways to categorize these generations.
Okay.
You get it? So if it is based on architecture, then what you are seeing in the module fits that purpose. But then if it's a different paradigm, then you have to go by what they are saying.
Okay. Okay.
Okay.
A bit clear. Thank you.
Yeah, you're welcome. All right, so moving on to the second generation, as I said earlier, this is where the operating system was actually discovered. And however, it has a limitation in the sense that it only can perform or handle a program or task once at a time. That is, it cannot multitask or multi-process any information that you give to it. And with that, this is some of the features that came with it. The on and off switches, which are used to control them electronically. And then this is where we started building the high-level languages. And then we have the float point arithmetic operations as well. So during this period, the second generation, these are the features that came along with the architectural design, where we first started getting the concept or discovering an operating system within the computer structure. And this came with the on and off switches that are controlled electronically. And then we have the high level languages. I believe you are doing programming. So when you get to programming, you will learn more about the high level programming languages or languages that are used to design the computer architectures. And then we have float point arithmetic that were also built within the second generation as well. Right, and then moving on to the third generation, this brought the improvement in the previous years in terms of the architectural design. And in this instance, they moved further and used integrated circuit. And then this circuit consisted of microprocessor chips made of thousands of transistors. So they move on and started using the integrated circuit, and the circuit has microprocessor chips, and these chips are made up of transistors, right? And these are the features that you can find within the third generation semiconductor memory. The size of the computer was drastically reduced. You remember earlier we spoke about cost here in the computer architecture design. More or less, the bigger the machine or the larger the machine, the more resources or costs you're going to incur. And then as the size reduced drastically, then the cost component also reduced. And then also there was multiple computer models with different performance characteristics. Earlier on, the computer model was just one because there wasn't an operating system in the first generation, but as operating systems evolved in the second generation, then we could create models of different computers with different performance characteristics within the third generation. Robert, do you want to go and sleep by asking that are we recording the session? All right, so let's move on and talk about the fourth generation.
No, please, but just for future references.
Yeah, I understand. So some books might move further and add fifth generation, but we are going to end here with the fourth generation. And this fourth generation presented a very large scale integration, and then also ultra large scale integration technologies which facilitated the process in combining millions of transistors. So this is where, Robert, this is where personal computers were actually created. And then we improved further and started using data communication between the computer systems. And then also we had a single chip processor and a single board computer emerge. That is, we could say here in the fourth generation, that is where we started having the motherboard. And then the processor within the computer system that could process millions of information. Charles.
Sir, please, I wanted to know the difference between the ultra large scale integration and very large scale integration.
Please, after the class, we're going to look for it, right? Is that clear? Right. So if it is a concept that you don't understand, that one can be explained. But these are standard let me say standard tools or whatever it is that you can just search on Google or anywhere to get an understanding of it. Is that clear? Because if you are supposed to be explaining where, then someone will ask me, what is a transistor? And then we are deviating from computer architecture to more or less like physics and any other stuff. Please, are we clear? All right. So these are the features that we have in the fourth generation of the computers or computer architecture. As I said earlier, you might have the fifth generation as well, but then let us end it here. You may go and read about the fifth generation and then see, but in most cases, the differences between each of the generations are not that much, especially in this modern era. Now, people are moving on from the hardwares that we have to bring another generation, which talks about the artificial intelligence generation and many other stuff. All right. So now let's talk about the von Neumann's model or von Neumann's architecture model. Felix. Felix, your hand is up. Are you speaking to us? All right, so the Theophilus.
Sir,
Talk to us.
please, in the other models of the other books, there is fifth generation.
Yeah.
But with this model, I'm not seeing fifth generation.
Okay.
Does it mean computer architecture ends at fourth generation?
I think I said we have fifth generation as well. No,
Okay.
we more or less don't expect us to feed you with everything. So you can read outside to add the various generations to it. That's all.
Okay.
Yeah.
Thank you.
Okay. Felix, your hand is still up. Yeah.
Yeah, I'm asking about the features of the fourth generation. The first one on the slide, it is creation of the person computer. Is it personal or person?
Personal computer, yeah.
Okay. Thank you, sir.
Creation of personal computers.
Okay.
Yeah. All right, so let's talk about the von Neumann's architecture model. And let me say, this is the architecture that most computers these days ride on or reside on. And it was mainly developed with the concept of storing a program in memory. And you realize in all the computing systems that we have these days, when you load a program, it stores the program in the computer memory before the CPU or any other process can be done to it. So realize that this von Neumann model is what these modern computer architectures are basically using. So within the instruction data and the program data are stored in the same memory. Instruction data, what is the computer supposed to do? And the program data, what is it supposed to do to what should it work on? What should the instruction work on? All of these are in the same memory. That makes access to the information very much easier compared to the information stored in the hard drive, and then you trying to retrieve from the hard drive, make it, the communication is very long. But then if everything is inside the memory, it is very easy to fetch the instruction, fetch the program data, perform your arithmetic or logic operation on either of them very much efficiently. And with this von Neumann's model, the basic operation is what we call the load and then store. The load and then store. So the load operation will read data from a memory location, whereas the store writes a value to a memory location. And I believe all of us know read and write. All right. So this is the basic operation that can be found in the von Neumann's model. And if you realize this new generational computer, they all have this feature where you can read from memory, and you can equally store or write a value into the memory. Robert.
Yes, sir. Just a quick one.
Yeah.
Is it this model that is that enable us to conduct forensic investigation to devices when there is suspected crime?
Can I get you clearly?
Taking it from the model,
Yeah,
by saying
okay.
that is where we have the store, the storage is coming from, concept of storing a program in the memory.
Yeah.
So yes, when I'm asking, that is it where the origin, that is it this model that enables us to conduct forensic investigation today? Should there be a suspected crime on any device?
Oh, okay. So should I say yes or no? Let me say
because
yes.
I'm looking at issue where it's able to load and store in a memory.
Yes.
So it means that I can get back later with whatever technology to able to get whatever information that has been stored in there.
Of
For
course,
that matter,
yes.
I can able to track back when there is any suspected crime on a particular computer.
Yes, that is very true. Remember, let me just say this. Whenever you download any information onto your hard disk or any other memory device and you delete it, don't be deceived. It is not deleted, right? Because in a way, when you write onto the memory, it sticks in the memory. And then in a similar way, when you stores, it stores in the memory. So it doesn't necessarily override the one that you have written, but it's more or less innate. But the architecture that we have currently in respect to the, what's the name? The UI that we have, the interface that we have doesn't go deeper to read information that are being deleted. So if you delete any information from your hard drive, there are still tools that we can use to get access to them. So yes, in a way, what you are saying is true. That can be used to conduct forensic audit on people, devices, and other ones. However, this same model can be used in a different way to still get information that is deleted from a computer system or any other system that we are using. So people who are programmers can actually use the same load and store methodology, write a program which will make sure that any information will enter in any system that is being built cannot be deleted or can be traced, even if it is deleted. Right? If somebody is asking what happens if the hard drive is formatted. Remember, everything that is digital, more or less, cannot be hidden, right? So please, the various devices that we use, especially these days where we have this cloud storage and all those stuff, as soon as you upload the information onto your hard drive, the cloud storage devices picks it up and stores in their server. You might have deleted it or formatted your hard drive, but they have it somewhere else. And they can trace your digital footprint, and then they have it over there. So please, it is very important to take note that information you delete from your hard drive are not actually deleted. They can still be retrieved. All right. Theophilus.
So, about the memory, but
Yeah.
it is said in the models like
Yeah.
that the memory is a volatile, meaning
Yeah.
when there is power loss, every
Yeah.
data is on. So
Yes.
why is it that the data is still on the computer?
Why is it that the data is still on the computer?
No, the data which was stored is still on the computer because
Yeah,
the
so
memory is.
yeah, so
What if
we have two types of memory, right? So we have the primary and the secondary memory.
yeah.
So every program that is running is on the primary memory, or what we call the RAM.
Yes.
However, every information that is being saved doesn't stay in the RAM. It moves to your hard disk or the secondary storage.
Okay. Yes.
You get what I'm talking about? So yes, if you run the information in the memory or the RAM and it is not saved, that is fine. But these days, some computers, as soon as the machine goes off, it can write onto your secondary storage. Just for you not to lose the file, yes. Or some of them, I mean, Word document is an example. You can activate an auto save over there. So in every second, it saves your information in it from the RAM to your secondary storage.
Okay.
Yeah. So for the RAM, yes, there's nothing in the RAM when the computer goes off. But then on your hard disk, that is what I'm talking about.
Okay.
Yeah.
Thank you.
Okay. All right. So let's look at the memory unit. And I believe we all understand memory unit or memory, right? Who can help us understand what a memory is? Yeah. Anybody? We all have memories, right? So what is it? Samuel. Samuel Ruby, tell us what a memory is.
Yeah. Okay. It is the temporary storage device of a computer.
Temporary storage device of a computer system. Okay. Okay. All right. Anybody else? Yakubu. Yusuf.
Thank you. So, with regard to the memory, I would say that in humans, maybe I will relate the memory to the work of the brain. Because I believe that maybe it's the brain that information of the future. And then with regard to computer, I would say is the component that keeps information for future purposes.
Okay. All right. Thank you so much, Yakubu. All right. So all that you said is correct, but then in technical terms, we normally say that memory is a collection of storage cells. A collection of storage cells. So for instance, if you have, let me see if I can annotate on the screen. Let's see. If you have a block like this over here. So this could be the hard drive that you have, but then the storage cells could be these various boxes that we can find in here, and in it we can store information into each of them. So this happens to be the storage cells that we are talking about, and they are merged together with associated circuit, and this helps to transfer information in and out of the storage device that we are talking about. So storage cells that are associated together with the help of a circuit, and then it can help us transfer information in and out of the storage. However, in this case, we are talking about the memory that is in the computer system, or the RAM. Let's take it that way, the RAM. So the RAM will help us to be able to transfer information in and out of the RAM storage. So in is from the hard drive to the RAM, and out is information is processed already, and now we need to move it out of the RAM to our secondary storage device. And in this instance, the memory stores binary information in a group of bits, that is 0 and 1s. In most cases, we call it words. So a group of binary information in a group of bits, we call them words. And then within the memory unit itself, we have a component in there that helps the memory and the CPU to communicate to each other more appropriately. And some of the components are the MAD, and then the MDR. And normally consider on top of the memory, on top of the memories that we have. So the MAD is a memory address register, and then the MDR is the memory data register. And as I said earlier, these are the two interfaces to the memory. And the processor unit get data to and from the memory through these two interfaces. Because we said earlier that the main purpose of the memory is for it to be able to transfer information from and to from the hard disk that we have, and then to the memory, and out of the memory to the hard disk. So this memory address register and then the memory data register will help us to be able to do all these processes. And this component also contains what we call data and instruction sets. These two components contain what we call the data and then the instruction sets. So during the execution, the instruction is loaded from the memory and it is decoded. So after it's loaded from the memory, which is the hard disk, it is decoded, and then appropriate operand is from the memory, and eventually the instruction set is also fetched. All right, so this is how the memory unit basically looks like. So we have the memory unit at the center, we have the various addresses and the data, we have the controls, the address bar at the top, and then we have the data buses. So the address bars basically, let me say, keep or load the address of the instructions that we have, either the instruction data or the instruction set. It keeps the address of all of them. And data button is able to communicate with the CPU and then other component of the system, so that information can be relayed or transferred from the memory to those components, or from those components to the memory, so that the CPU can process them much more efficiently. Please, how we are clear? Any question? Any question?
Sir, please, I would like to know the difference between the address bus and the data bus.
Address bus and the data bus. All right, so the address keeps the address of the instruction set or the data program. You know, it's very important for the CPU or the computer system to know the location of every instruction set that is within its control. So it's the duty of the address bar to locate or to store more or less the addresses of those instructions, so that when you want to fetch it, they just get the address and then they fetch it into the memory unit, and then it starts the process with the CPU. right? And the data bus also more or less communicate the data to and through the memory unit, and then the other components that are connected to the CPU and the memory as well. I don't know if you get it.
Yes, sir.
Okay. All right, so I believe all of us are very much familiar with the CPU of the computer system. And then in most cases, some people say that it is the soul of the computer, or some will say it's the brain of the computer, which can be understood as an electronic circuit, which is primarily responsible for executing instructions of the computer system. So in some cases, we call it microprocessor or the processor. Either ways are appropriate. So any electronic device or any electronic circuit that is responsible for executing instruction of the computer system, it is called a microprocessor, the processor, or the CPU. Right. So now, do we have a CPU in a calculator? Do you have a CPU?
Yes.
Yes, sir.
Samuel, your hand is up.
Yes, sir. I can say it has a CPU because it has the ability to process data into information.
All right. So what of a rice cooker? Does it have a CPU? Joseph.
Yes, it has a CPU.
Can you further explain?
It has a timer which you can set the number of minutes you want to warm or how you want the information, and when it is instructed and it's finished processing, it gives you a feedback on the process.
What feedback is that for rice cooker?
Yes. So so the feedback is when it's well cooked, you'll see that the cooking this thing will eject itself and then and move into a warm control.
Oh, okay. Please, anybody else to second or support Joseph's claim that rice cooker has a CPU? Joseph is alone. Oh, please, someone should help us. Okay, Theophilus.
Yes, sir.
What's your
I
take?
think it's true. I second him.
It has a
because
CPU.
It executes instruction. After timing it, it process and give you a feedback like you time it. That is an instruction given to the rice cooker. So after the cooking, it gives you a feedback that the cooking is done. So it has processed the data into an information. What is the meaningful way?
Okay. Anyways, Joseph.
With some of the rice cooker we have currently, some even have regulators that can indicate how warm and how fast you want the food to be done. So you are able to tune it to the number you want, and then you can also deregulate it at the same time.
Okay. All right. Joseph.
Yes, sir.
Please talk to us.
Oh, I just finished speaking, sir.
Oh, but your hand is still up. That's what I'm asking you.
Oh, okay. I lowered it, but I was saying that it has some of the current rice cookers have regulators how fast and how you want the substance to be cooked fast. So you can regulate it in a higher form and you can deregulate it the way you want it. And then when it's done, it gives you a feedback.
Robert.
So now the new rice cookers and other things could even be hacked and be remote controlled from elsewhere. So it means that there is even a processor in it. That is why it is able to shut down and then do respond to these kind of commands. So I think the new ones definitely have this processor unit.
Processor, okay. Wajo Posomche Ebenezer.
So rice cooker have processor because it receives input data, and as it will bring an information, you have to process it. So rice cooker have processors.
Okay, Cliff is the last person. Cliff.
Yes, rice cooker have processors, but they are not like the normal thing that we know. They are core circuits, and they are core circuit, integrated circuit that all the processes are being embedded into it. So rice cooker does not have a form factor to contain a CPU, but they have integrated circuit. Thank you.
All right, thank you so much. So I think we can find a solution from here. But then if you ask such a question, you just have to look at the definition of a CPU and then you relate to the core technologies that are in the definition to the concept that you are talking about. That machine has the same, more or less, core definitions in it. So a CPU can be an electronic circuit which is responsible for executing of instructions. And I believe Cliff said that the rice cooker has its integrated circuit in which the processor is embedded into it, right? And more or less, we still have an instruction. It can still execute instructions that are given to it, just as Joseph and others explained. We set a timer as the input and then execute that instructions for us. So we could say that the rice cooker, yes, has a CPU, but not the form factor of an actual CPU that we have in our personal computers and then the desktop that we have. All right. So for a CPU, these are the various components that we have. The control unit. We will have one or more arithmetic logic units, and then we also have registers. It could be multiple of those registers in it. And for a control unit, I believe all of us know what a control unit is from basic school. But then let's try to understand it from here. So the control unit basically orchestrates all the executions of the program. That's more or less controls all the executions that are running on the computer memory or the CPU that we are talking about. And then this control unit or CU is made up of two important components. One is the instruction register, and then the other one is the program counter. And when we talk about the instruction register, it contains the current instruction for execution. The CPU has the instruction register, which contains the current instruction for execution. And then the PC, which is the program counter, contains the address of the next instruction to be executed. So these are the two components and their differences. And in this, we could say that the CPU basically reads instructions from memory, which is stored in the PC, the program counter. It also interprets instructions and generates signals that tell the other components of the computer system what to do. So this is how more or less the CPU and then the memory communicate to each other so that the information can be executed. So notice the two main components that we have, the IR and then the PC, and their differences or their functionalities in the control unit. All right. And then we have the arithmetic logic unit. This basically helps us to perform some required micro operations for executing instructions. And then the ALU allows arithmetic operations, which is the addition, subtraction, multiplication, and others. And then also logic operations to perform on the data. And some of the logic operations include the AND, or and NOT operations. All right, so now let's talk about the registers that we have. So the registers are basically high-speed storage locations that are found in the central processing unit. So probably it could be asked that does the CPU contain storage locations? And I believe you should be able to tell us that yes, registers are more or less a storage location that are in the central processing unit. And all of the data that are in the CPU are supposed to be stored in a register before they can be used. So if you want to execute a program and the program is not found in a register, that means it cannot be executed. Please, are we clear? So maybe after the class, you can go and sit down and understand the difference between the three that we spoke about: the control unit, the arithmetic logic unit, and then the registers. How they are different from each other and how they work together to make sure that our operations or instructions are executed smoothly. So some of the registers that we have include the current instruction register. We have the accumulator, instruction buffer register. For the CIR, this holds the current instruction during processing. So any instruction that is being executed or that is in execution can be found in the current instruction register. And then we have the accumulator, where intermediate arithmetic and logic results are stored. So this one stores intermediate and arithmetic results. And also we have the instruction buffer register. So for this one, instructions that is not to be executed immediately is placed in the instruction buffer register. So if you have an instruction that is not to be executed at that point in time, but then it will be executed subsequently, then the computer is designed in such a way that those informations or instructions are stored in the instruction buffer register. Please, I hope everybody is clear here. All right, so let's move on to input and output. Anybody to help us understand what input and output are? I/O devices or I/O? Anybody? I/O devices. Okay, Theophilus.
Okay, input devices are devices that is used to enter commands into the computer system. And the outputs, they bring out or they display the information.
Okay.
That is processed by the computer.
All right. Anybody else? Thank you so much. Samuel.
Yeah, I will also say that input devices are computer peripherals that send data and instructions to the computer to process. And then the output also displays the information after it has been processed by the computer.
Okay, thank you so much. We have another one. Yakubu. You see.
Yes, sir. So, with regard to input devices, I would say that these are devices that we use to take data into the computer for processing.
Okay.
And with the output, I'll say that those are devices that gives out information after it has been processed by the computer. So the input devices, if I should give examples, I can say that maybe we use keyboard to enter mathematical questions. And then the processor will take this and the answer is given out by the output devices like monitor or printer or projector. That is what I have to say.
Okay. All right. Thank you so much. Melly. Yeah, I was saying. All right, so let's proceed to
Sir, please. So the input devices, these are devices such as the keyboard or the keyboard, the scanners. They send data or signals into the computer. Whilst the output devices, such as printers and speakers, they receive data from the computer for user interpretation or storage, please. Thank you.
Sir. Hello.
Jefflos.
Yes, sir. Putting both together, I would say they are responsible for getting data in and out of the computer memory.
All right, yes, that's correct. So input output basically means that devices that can be used to get data in and out of the computer system or computer memory are what we call the input output devices. So the input unit basically provides data instruction to the system. And more or less they process data in the CPU assigned to the output unit. You have to notice that each of these devices have their own interface. And in most cases, a set of registers like memory, MDR, and then the MAR. Right, so input units and output units are more the same as output devices and input devices. So if you see them anywhere, explain input unit, you should be able to understand and explain them. So these components are mostly linked through a set of signal lines called buses. I think we saw one earlier. So this input unit and output unit are mostly linked together through signal lines that we call the buses. And then the main bus carrying data are the control bus, data bus, and address bus. And then the control bus includes signals that allow the CPU to connect with memory and then the input output devices. So I have this diagram here for you to study and probably ask any question that you understand. So please kindly study the diagram, and then when I come later, if you have any questions, you can ask. All right, please, any question? Any question, or we are okay with the diagram? Frivolous.
Sir, I want to understand the bus. Are they the cables that is connecting the various components to the CPU?
If you see cables is too weird. No, they are, when you open the computer system, you see some lines that are more or less like, is it brown or gray? Those are
Yeah.
the buses, yes. Even on mobile devices, they are there.
Yes. Okay.
Those are the buses. They are not cables. They are just signal lines.
Okay, thank you.
So they send the instruction from this output or the input devices to the CPU or the memory. That is all.
Okay, thank you.
All right. Is there any other question? Okay, Joseph. Joseph, we are waiting for your hand is up.
Yes, I mean the arrows that have been indicated on each side. If you could just throw a little light on for understanding.
Which of them?
Yeah, I think because from the explanation of the iOS system,
yeah,
instruction is given from the input with the input devices.
Okay.
Which goes into the. So I want to understand when the instruction is given first. Does it go to the address bars first before it then goes to the memory?
Okay, so it depends on which instruction is given. That is why you have the three lines. One of them which is connected only to the control bars, and one which is connecting to the address bar, and one which is connecting to the data bar. So it depends on the instruction that is given. Then the input output instruction move to the appropriate signal lines, and then it goes to the memory or the CPU.
Okay.
Yeah. So the same applies to the memory as well, because we said there's information to and fro the memory. So if you have information as well from the address bars to the memory, and then also from the data bus to the memory as well. So the arrows from each means that it can flow from that data bus to the memory, and from memory to the address bar or data bar or control bars as well.
Okay. So
Yeah.
that means it depends on the type of instruction you've commanded.
Exactly. And which bus should the instruction follow to get to the CPU?
Okay.
Yes.
Okay. Thank you, sir.
Okay. All right, so let's move on and let's talk about the data bus. So this is let me say, a component of the computer system that carries the data or information being transferred between the processor and other component. Between the processor and other components. So that's the data bus. And it is very important to notice that it is bidirectional, which allows for the transfer of data from one component to another within the computer system. That means that it can flow from, let's assume that we have the CPU and then the memory. So the data bus can communicate to the CPU and at the same time the memory, because information can flow from either end. That is what we are saying. It is bidirectional. And it can host a lot of bits of data at a particular time for the data bus. Data bus can hold many bits of data at a time. All right, so let me see. So this is an example of the data bus that we have. right, so we have the data bus over here. So we basically serves this situational awareness component of the system that we have. We have the planning, the vehicle, the lodging, and many other components over here. So whenever the instruction is given, yeah, the instruction will move through this data bus, and then when it gets to the appropriate component that is going to, it will just go there and then start the execution, whatever instruction that is within it. And it could have the address bar. For the address bar is also a subsystem of the bus system that carry memory addresses from the processor to other components, which may include primary storage to the input or output devices. So it carries memory addresses from the processor to other components, and it may include the primary storage to the input or output devices. So you have to notice that the address bar connects the CPU and other peripherals or internal pieces of computer systems and carries only memory addresses. It carries only memory addresses. And this is used to identify where information is being sent to. This is used to identify where the information is being sent to. And as opposed to the data bar, this is unidirectional. That is, it moves in one direction. You can't have addresses from one, let's say, CPU to the memory. It can't happen that way. So if the address bar is moving from memory, it moves to a CPU, but then not CPU to memory and memory to CPU. That's not going to work. And one of the main importance that it helps the transfer of data between devices that are known to hardware addresses of a physical memory. So it helps the transfer of data between devices that are known to the hardware addresses of the physical memory. So that is that for the address bus. Now I think we have the control bus as well. So the control bus also describe aspect of how the information is being sent and in what manner. How the information is being sent and in what way or in what manner. So it carries the signals from the processor to other components. And it can also coordinate activities between various devices to prevent what we normally call the data collision. Please, any question on the address, the various buses, the address bar, the control bar, and then the data bus? Any question? All right, so let's look at some technologies of the bus system. We have the bus with bus type and then the bus operations. So basically, when we talk about the bus with, it refers to the data and addresses within the bus system. Data and addresses within the bus system. That is what we call the bus with. And for system performance to improve, the wider data bus, as we can move more bits in parallel, the better the device that we are using. So if you have very wide, bus, let me say that way, a very wide bus, either the data bus, the address bus, or the control bus, then it means that you can transfer more bits of information or bytes of information through the bus to the various components of the computer system. So for us to be able to do this, we basically add more address lines to the bus systems. That is why these days in most of the computer systems, when you open, you have so many of the signal lines that are on it. That means that the bus width is very large enough that we can push in so many signals from either component to the other. Please, are we clear?
Yes.
All right. Now let's talk about the bus type. I don't know if you spoke about the bus type, but then we have two basic types of the bus type, which is the dedicated and then the multiplexed bus type. Did we speak about it earlier? I don't think so. So dedicated bus type basically means that this particular bus is dedicated to, let's say, transferring information only from CPU to the memory. That is, we have dedicated this bus to carry information from CPU to memory only. Nothing else can be passed through that particular bus, and that is what we call the dedicated bus type. I hope it's clear.
Over the bus type again.
Yeah, so I was saying that we have two main types of bus type. That is, how do we want the information to flow from one component of the system to the other?
Okay.
Right. And then I'm saying that we have two of them. One of them is the dedicated bus type. And I was explaining that for dedicated bus type, it means that we dedicate one more or less instruction to only flow through the bus. So assuming that we have communication between CPU and then the RAM, we can design a bus that is only responsible for communicating information from a CPU to the RAM. Please, are we clear?
Yes, please.
However, with a multiplexed, it means that we can allow multiple signals to pass through that particular bus. So multiple signals, more or less, share the same communication channel. So if it's about transferring information from CPU to the RAM or CPU to any of the IO units, then IO units, we have a single bus that is able to accept communication in that sense. Then we call that the multiplexed bus type. Arafat, are you okay? And is everybody okay with bus type? So notice that we have two types of them, the dedicated and then the multiplex.
All right.
It's just specific to one signal. However, multiplex means that it can pass through the bus with so many signals or so many signals sharing the same communication channel. That is a multiplex.
Thank you.
Okay. And one other technology or terminologies is the bus operation. The bus operation. So this basically talks about which operations can be performed within the bus system, which operations can be performed within the bus system. And we have listed some of the operations down here. So some of them is the read operation, the write operation, the block transfer, read, modify, write, and then the interrupt operations. So which operations can we perform on a particular bus? That's what we call the bus operations. And as I said earlier, some of them are the read, or you can read information from the bus. That is, if it's a data address, but you can read the address that is flowing through that particular bus. If it's a data bus, you can read the data that is on the address bus. Similarly, if it's a write operation, you can write information onto the address bar for it to carry to the destination that we are talking about. You can only block transfer of signals from one component to the other. You can have read, modify, write operations, and the interrupt as well. So these are some of the operations or bus operations that we can perform within the bus system. And also these are some functions of the bus system. But I have to notice that different types of bus are used in the computer bus scheme. And depending on its purpose, each of these buses is allocated to carry certain signals or information and data as well. That is from one component to the other. And some of the functions of this bus system are addressing issues, more specifically for the address bus, signal control, providing component with power, scheduling system time, and data sharing. So when we talk about the complete bus system, these are some of the functions it normally comes with. Please, are we clear? Any question? All right, and then we have one other concept in the computer architecture or software design, let me say that way, which is called the upwards compatibility. And let me say, you know, in the previous days, when a software is built for a specific computer architecture, no other computer architecture can be able to use that software unless it is built again to suit that particular architecture. But in these days, such thing is fading away with the help of the upwards compatibility. And what this normally means is that when we build an application, we make room for people that are still using the old architectures to be able to adapt or use the, let me say, the newly built architecture on top of the old ones that we have. Or we could say that those people can upscale their old architecture to the new one that's available. And then by definition, the upwards or forward compatibility allows users to upgrade to faster, more capable machine without necessarily rewriting the software that runs on the less capable ones. So you have, let's say, Windows 7 machine that's available. And then someone has built an application that you want to use. In that instance, this upwards compatibility means that you can actually use or upgrade and use that software without necessarily rewriting the software all over again. Remember, as I said earlier, when you write for IBM machines previously, it only runs on IBM machines. But these days, with the help of the upwards compatibility, that is not the case. Please, are we clear?
Yes, sir.
All right. So some of the pioneers of this upwards compatibility is the IBM Industries, and they came with a concept called a family of machines with 360 series. And then This main issue happened after they had 4 incompatible lines of computer, and then each of the system had its own instruction sets, input output system, and secondary storage assembly, compilers, and other libraries. So with the upwards compatibility was fundamental for them to upgrade or use a newer version of the system that had been built on top of the old ones, without necessarily stopping to use the old computer systems that they have. And they named this particular concept family of computers, in the sense that you have a very old machine, but a new development that has come, you can still run them on top of the old machine that you have. That is what we call the upwards compatibility. Is any question? All right, so let's talk about the levels of computer architecture. And when we talk about levels of computer architecture, we're basically talking about the hierarchy of the architectural design for the computer system. And we progress from the top level downwards. And then in that process, we come to a point where we call the abstraction. That is where more of the internal or the core structure of the computer is more or less exposed. So you move from the top, we move down until the level becomes abstract. And abstract in the sense that the internal or the core structure of the computer is basically exposed. And I think we have 4 or 5 levels of them. So let's talk about them one after the other. One of them is the user level, which is the highest but the last of the computer system hierarchy, which is basically consisting of the users and then the executable programs. Now, at this point, it is the user who interacts with the computer by running programs on it. That is the first level, the user level component. And then we have the high level language, where at this level, the programmer sees the data type and instruction of high level language, but needs no knowledge of how those data types are actually implemented in the machine. So those of you who more or less want to write computer programs or are writing computer programs, you might be using some data types, but you don't really care about how those ones are built. You don't want to know how the integer is built, how the floats are built. Your main goal is to be able to use them and use them effectively. So at this point, that is what we call the high level language. So anything else that you write, it is a role of what we call a compiler to map the various data type that you have written an instruction from the high level language to the actual computer hardware. Your duty is to be able to use the data types appropriately. Whatever that is done to execute the instruction, that is not your concern. And in this particular level here, it provides a convenient and interface an application engine which helps user produce results for a given specific area. And in this instance, we use some languages in this process. And some of the languages are what we call the high-level programming languages, such as the C, C++, or the Java. And we normally call this one a keystroke. So those who are into programming, you mostly hear of keystroke. So keystroke basically means that we're actually writing a computer program with the help of high-level scripting languages, right? So the high-level, the person who designed the computer architecture, in the process of giving out the instruction, he doesn't want to know much about anything that's happening, especially when it comes to data type, instructions, how the code is going to compile. That is none of your concerns. Your duty is to be able to use those data type quite properly and appropriately. Then the machine will take it from there. That is, the compiler will have to map data types and instruction from the high-level language you've written to the actual hardware that you have within your computer system. And some of the high-level languages we have here are Java, C++, C, C#, and many other that you may go and look out for. All right, so now we have another level, which is the assembly language. This is mostly used by system programmers. And here there's no interface or convenient interface for us to use, as opposed to a high-level language. So the assembly language is very much detailed language, which helps the system users move information around in computer architecture in a specific way. So here, the person is actually interacting directly with the hardware of the computer system. And this was very predominant in the early stages where Windows didn't have an interface. So most people were writing commands to be able to interact with the kernel or the hardware component of the computer system. Right, so the compiler basically translates the source code to an actual machine instruction. And in some cases, we call them the machine language or machine code. And at this point in time, there's high level of speed compared to the previous high level language, because here you are communicating directly with the hardware component of the system. And that makes it very much faster compared to using the interface and other stuff. Please, are we clear? All right, so let's move on to the control level or the microarchitecture. So this more like provide an interface or serve as an intermediary between the assembly language and the abstraction of the hardware. So with this one, it is a control unit that effects registers transfer. And then it does it by control signal that control transfer data from the register to register. And then in most cases through a logic circuit that transforms it in some way. So the control unit main purpose is to interact or interpret the machine instruction one by one, causing the specified register transfer or other actions to occur. So at this point, we are communicating more or less directly with the various registers that are found within the control unit. You know, previously with the previous one, we were talking about having access to the input-output device, that is the hardware component. But here we have moved beyond the hardware component, and then we are accessing the registers that are within the control unit. Means that information is going to be much faster. Alex, do you have a question?
No, sir.
Do you have a question?
No, sir.
Is any question on the control level or micro architecture? All right, so I think this is the last level that we have, which is the functional unit or the instruction set. So this is the interface between the lowest and then the hardware. And Enoch.
Yes, sir. I heard you saying this one is the last level.
Yeah.
But in other textbooks, there is after this one there is other one.
Yeah, what's the name?
Digital logic level.
Digital logic level.
Yes.
What did they say about the digital logic level?
They are talking about they said it's about zeros and ones.
So it's the same thing. I mean, the functional unit or instruction set uses make a binary machine language program works correctly, including instructions. So at this point, we are interacting directly with the instructions that are in there, and every instruction that we write is zeros and ones. Exactly. So probably naming conventions are different, but then this is the last one that talks about binary machine language, zeros and ones.
So do you mean that the other book decided to take that one out of the instruction set?
What I'm saying, you don't understand. What I'm saying is that probably the naming conventions are different.
Okay.
You get, so the naming conventions might be different, but then this is the last one that speaks about using the binary machine language to operate or send instructions to the various components in the computer system.
Okay.
You get it?
Okay.
Yeah. So at this point, we are not dealing with high-level language like the C++, the Java we spoke about earlier, and we are not also interacting directly with the hardware or the registers. Here we are using the actual machine language, which we all know is binary, 0 and 1, to be able to have or communicate with the computer system that we have. And this is the fastest way to get all your information processed for you. So we are going to write a text on our interface. It will move to the next level until we get to the machine code where the machine understands the zeros and the ones. So in the olden days, this is what they were using to write computer programs, the zeros and the ones. But as time goes on, they started building the high-level languages that we human beings can understand and make things easy for us. Is we clear?
Yes.
So yes, in some books, truly, there could be some other ones, but then look at the definition over here. Are they correlating? That's why I asked you, what are they saying about the digital logic? And then you mentioned zeros and ones. Obviously, we have binary machine language, which we all know is zeros and ones as well. So maybe the headings might be different, but then the content are the same.
Okay, but in the book I'm talking about,
yeah.
They have the digital logic level and they have instruction sets.
So the instruction set, what is there?
Okay, so the instruction set, the book said that is where they program the instructions for the computer.
Okay.
That's what the book said over there.
And the digital.
And the digital, the book said that's where the zeros and ones are. The binary numerals are.
So when you are programming for the computer with the instruction set, mind you, the instruction set is the instruction set cannot be text. It cannot be characters. It is supposed to be zeros and ones. Those are the instructions the computer truly understands. The CPU and the processors. If you are programming in the zeros and the ones, more or less you are giving instruction to the computer system. So maybe they decided to separate instruction set from the zeros and the ones. That is their own case. But here We are combining them because we assume giving instruction is more or less programming the computer to do what you want it to do. And at this point, it is zeros and ones that we are using to give the instruction to the computer system. Is it clear?
Yes, it's clear.
Any other concern or question? Some people have gone to sleep because we are recording. All right, so let's move and talk about logic gates, transistors, and then wires. Okay. So this is one of the, let me say, within the instruction sets, we have the logic gate, the transistors, and more somehow the wires in there. But in these days, the computers that are being built, the wires are fading away, right? So this is the lowest level at which any semblance of computer high-level functioning is visible at the logic gates and then transistor levels. It is from logic gates that the functional units are built, and from transistors that logic gates are built. So we build the logic gates from the transistors. I just believe we have to talk about the logic gates before you do the presentation, because that one is a little bit what's the name, tricky. So if you'll be doing that for your presentation, then you have to be very careful and learn them properly. So before you get a logic gate, we need to get transistors. So from transistors, that is when we are able to build the logic gate. The logic gate implements the lowest level logical operation upon which the computer functions depends on. And in this case, the digital processes are expressed in terms of functions of zeros and then ones. So some of the logic we have is the OR, the AND, the NOT, the XOR functions, and the others. So at this point, that is where the logic functions, the transistors or the wires are basically built, right? Please, any question on logic gates, transistors, and wires? As I said earlier, I hope we will get to logic gates and then you understand how they actually work properly. Any question? Enoch, your hand is still up.
Okay, I want to know whether this one is only about the hardware part of the computer, right?
Which one?
The one you are talking about, the transistors and the wires level, the transistors level.
Yeah, so those are part of the architectural design of the computer system. The logic gates and then the rest. Are we clear?
Yes.
All right, so finally, let's talk about the computer system and then you might leave here. And I believe all of us know what a computer system is, which is basically a set of devices that accept input, output, and process the data and store them for us. And these days, computer systems are currently built around at least one digital processing device. That is mostly what we call the CPU, one digital processing device, or let me say devices, so that they can process our information or signals or input that we give to the computer system. And this diagram shows a typical complete computer system where we have the server, we have the monitor, we have the keyboard, and then when you open the system unit, you have the motherboard there as well for us to see. So this is a typical computer system that we can find. And with a typical computer system, you should be able to find all the components of the computer system in it. That is the input output unit, the processors, and then some other ones that are going to help or improve the functionality of the computer, which normally called the peripherals. So let's break this computer system down into their various components. And there are only two of them. So the first one is the computer hardware, which I believe all of us know, the physical part of the computer system that we can touch and probably operate on. And with the computer hardware, we have the output unit and then the input unit as well. So the output unit basically present to us the information that we have processed, and the input unit takes the instructions for us. And you know some examples. So some examples of the computer hardware are the input devices and the output devices. And I believe all of us know them, so please go and read them more. And then we have the software as part of the complete computer system. Mind you, can have a computer hardware, but then if the softwares are not there, then it doesn't qualify to be a computer system. But if you have your PC without an operating system on it, you can't really do anything about it. So it's very important for us to classify or notice that a computer system should have computer hardware intact and then also software as well before it can be a complete computer system. So softwares are basically data and instructions that allow a computer to do a specific task or job for us. And we can classify them into two, which is the system software and then the application software. So the system software handles communication between the hardware system of the computer, or it coordinates the activities within the computer system. The examples of those system software are the almighty operating systems that we know, the antivirus softwares, the device drivers that we are much aware of. So that is the system software. And then for the application software, these are specific programs or instructions or applications with an interface for the user to interact with the system to provide a specific task or various tasks for the user to understand. And examples include the word processor that we are familiar with, the Adobe Photoshop, and so many others that we know, calculators, and all those stuff are examples of the application software. Please, any question over? Any question?
No, sir.
Frank?
No, sir.
Alex, any question?
No, sir.
Is any question before we move? We leave here.
Sir, it seems there are some diagrams you showed which are not in our models, the models we have.
Yeah.
Then you have to send your own to us.
It is the same thing. It is just that I didn't want, that the model is too much of text. So I didn't want to present the text for us to be seen. And we all can read, and that is why I just decided to bring the diagram. Yeah.
Okay, thank you.
Okay. Yakubu, Yusuf.
Yes, please, I would like to remind you, can you provide us with the course outline? Because sometimes when you have to do your own, then with the help of the course outline, I think you are able to stay on course than when you are just reading without the course outline. So maybe if the course outline is available, you can make it, you can give it to us so that it will guide our students.
All right, I'll share the course outline with you, but the truth is that you can't use 4-6 weeks to learn architecture, right? So it's very important, even if you have the course outline, you get some information, you read along. One of your colleagues was just saying, you read wide, you come on board, and then we speak about it. That is all. And I'll try to share the outline with you. Alex. Okay, Alex.
Hello, sir. Sir.
Okay.
Hello, sir.
Yes, we can hear you.
Hello.
We can hear you, Alex.
Please, I've sent invite this thing to you. Hello,
Okay,
sir.
I'll join
Please,
after
can you
the
hear me
class.
now? Please, I've sent this thing invite you. Please, can you? Yes, please.
Yes, I'll join and share the course outline with you. Obed.
So please, I'd wanted I'd wanted you to share the model with us, but since you said you were going to share it.
Your colleagues have the models already, so you can get it from them.
Oh, okay. The one I'm having is different from the one you were using.
I don't think so.
He said it's the same thing.
Yes, if you are not seeing some of the images, I didn't want to present the text for you for us to be reading.
Oh, okay.
That is the same thing, yeah.
All right. Then.
Okay.
Doc, are we
All right,
getting
so without any
the slides?
Getting
Alex,
Are we getting the slides?
We'll meet again next week and continue.
Okay, sir.
Everything is in the models. You have the models, right? The slides is just a summary.
Yes, please. Everything is in the show. Let's go by the model.
Yes, the slides is just a summary, but the questions might come from the model. So just focus on the models. And then I'll encourage you to read the models. If you come and you don't understand anything, you can go back and address them all. Alex.
Okay.
Sir. Hello.
Alex, we are listening to you.
Sir, please, the model, the one that we downloaded from the portal, are you talking about that one? Or because mostly some of the words and then some of. Hello, sir, can you hear me? Hello,
Yes,
sir, can you hear me?
We can hear you.
Hello.
Yes, ma.
Hello.
We can hear you, Alex.
Hello.
Alex, you can be heard. We can hear you.
Please, are you talking about the one that we? Please, are you talking about the one that we downloaded?
Yes, that's what I'm talking about.
I said the one that you are talking about, we downloaded from the portal. Please come again.
All right, so we'll meet next week and continue.
Thank you so much, sir.
All right, sir.
Okay, sir.
Okay, sir.
Alex, yesterday the course that was postponed to today, what time was set for it, please?
It was 6 o'clock. 6 o'clock to 8.
Please, which course is that, please?
Please, are we done for today?
Programming.
Programming.
No, today we don't have any class. So
All right, thank you.
today we
But
don't
I
have
thought
it.
yesterday one was postponed to today.
The operating system. Are you talking?
But it's programming.
No, we're supposed to meet
No, it's programming. Have you heard
one lady lecturer. We're supposed to meet one, and she
Yeah.
responded.
That's the
the
program.
operating system. No.
We've already done the operating system.
No, it was.
We've done operating system.
Yes.
So
it's
that's the
programming.
Okay. So are we called?
Alex. Hello, Alex.
Yeah. I am saying that are we called Savior? Yes.
Are we doing everything? Are we doing online next week?
Talk.
Are we doing online next week?
Yes. You said what?
I said,
Online.
are we doing all the courses online next week?
Yes, please.
Okay, sir.
Yes, please. Yes, please.
So Alex, and any lesson here?
Saturday we will be having 4 courses. The Sunday will be review. But by yesterday in the programming, in the lecture, I'm supposed to have the class with us.
Yes.
Yesterday, but so if we didn't make it, we can call her concerning that maybe the reason if you can have the class today there. So where's Xavier? Xavier. Hello, senior Xavier. Xavier. Hello, please, I'm calling. So Xavier, you know, you can call him for me. I'm trying to buy. He's not responding.
Please, can anyone help with the models for operating system? Please.
The operating system. I tried to call the lecturer, but I couldn't get him. The number he gave me, the number is not going to. But the WhatsApp one, there's the active, but the call one, there's not. So I don't know, maybe unless this week and we will lodge the complaint. So, no, we try the number as a right now.
Which course did you do in the evening yesterday?
In any of you guys, I did think I can reach. That's okay.
That means we haven't done programming.
Yeah. I try to reach him concerning the models program. No, we are not yesterday, but we're supposed to have it, but we don't know actual date. I mean, the day I want to have the ones that with us, I don't know. So if
you guys,
four heads can send in that, yeah, it's nice.
Alex,
So who has the number? Hello.
Alex,
Yeah. Who has the madam number?
I think you should check
The program, yeah.
the timetable. Their
Yes.
contacts are there.
So,
Please, can you share the group link with us? Shall we have your number to join?
but some of their numbers is not working.
Then you have to take their numbers from
Okay.
the other group.
I said the numbers, some of the numbers is not working. You know.
Oh, okay.
Like the same thing. No, what I'm trying to say with the number that is on the timetable, we try, but it's not working. We will call back, we're not going. But number,
Okay.
the number wasn't going to. So we don't know.
Can you share the group links with us so that
if
we
you can get
are not on the page
serious,
and join?
I mean, I heard that yesterday Sylvia called the madam, so I don't know if you can get him there. You can provide us the correct number. A group link. So which one you are in? Which one? Hello. Hello.
I've joined database management and then
hello
operating system, but for the rest, I don't have. I'm not in it.
Hello. Hello.
Hello.
Uh-huh. What about are you in that page?
No, I'm not on that page.
Hello.
I'm not on that page.
Okay. So, I mean, you have my number already.
No, I don't have your number.
Already. You have my number.
You can send it here. So I don't have your number. I WhatsApp you.
So tested me. Test me. WhatsApp.
Okay.
So that I can add you to that one.
Okay.
Hello. Hello. You don't have my number. Let me. Okay. Let me give you my number. 050 050 58 050 58 46 959. Hello. Hello.
I've gotten it. I've gotten it. Thank you.
No. Check it. Sure.